Good morning, everyone. Good morning, sir. So, our topic for today's presentation is static stability and how position of center of mass with respect to aerodynamic center affects static stability. Uh, for an aircraft to be stable, what we want is we want the moment coefficient to be less than zero with respect to angle of attack. So, change in moment coefficient with respect to angle of attack when it is less than zero, where we can say that the aircraft is stable. If there's no response, then it is unstable. Then it is neutral. And when basically it is greater than zero, basically any kind of any kind of gust, wind gust, any kind of small force can make the aircraft basically diverge from its current position, current orientation. We see that the aircraft is unstable. So as we can see, how do we ensure that the aircraft is stable, and how does the position of center of mass, center of gravity, affects that? As you see over, these are like critical points that we need to take into consideration. First one is center of gravity. It is the mass, is the point mass, which we can say is the distributed load of the entire aircraft we consider over there, and where the weight acts. The one is center of pressure, where basically all the summation of all the aerodynamic forces acting on an airfoil, that point is known as center of pressure. And the third is aerodynamic center. The aerodynamic center is the point where basically the pitching moment does not change with angle of attack. For example, when the angle of attack changes, the lift distribution over an airfoil will change. So the center of pressure will move, but aerodynamic center will not change for an airfoil. Uh, when it comes to supersonic aircraft, the aerodynamic center can shift due to the increase in due to the compressive flow. So let us move forward. So this is a fundamental case when the aerodynamic center is behind this center of gravity. So what happens in this particular condition is, so if the aircraft is flying at a trim angle of attack, and if we increase the lift, so that will basically with angle of attack, if we increase the angle of attack, that will lead to increase in lift, but that will create a restoring moment on the CG with due to the lift force, and that is basically a restoring nose down moment. So that means that this aircraft is stable. Uh, for uh, for for this particular this particular location of AC and CG. But if AC is ahead of CG, we can see that increase in lift, increase in angle of attack, increase in lift will actually make the aircraft move again more nose upwards instead of downwards. So it will basically, the aircraft will diverge, and that is the reason it is unstable. This kind of a situation is actually in fighter aircrafts, but for them we use fly-by-wire computers to prevent divergence. Next is why we use tail. So for a normal flying wing with no tail, the neutral point will be ahead of CG, basically an unstable configuration. What tail will does is it will shift the aerodynamic center for the entire aircraft behind the CG. So basically making the aircraft stable. Neutral point is the point, it is basically like just what is aerodynamic center for a wing. Neutral point is for the entire aircraft, where the lift, basically resultant lift of both the wing and the tail acts. So as you can see over here, since we are shifting the basically neutral point ahead of CG, it will ensure that our aircraft is stable. Whereas if we use canard and it shifts forward, that will make aircraft unstable. The second issue, how we derive the our stability condition. So this is a simple aircraft. We can see here is the aerodynamic center of wing. This is the tail, simple vertical tail. And if we take the moment around CG, we can come and divided by dynamic pressure. We can find that the stability derivative Cm alpha is basically dependent upon two terms. One is this is the distance between CG and aerodynamic center, and the other one is the wing tail coefficient and the wing part. So that is how we come into this part. And so what we need to ensure is the stability condition is we need to have that the Cm alpha should be less than zero. So increasing angle of attack should reduce our moment coefficient. For that we need that our H should be less than HL. That means our center of gravity should be less than the neutral point. This is for varying CG positions with angle of attack. So as you can see over here, if we so this is CG as 25% mean aerodynamic chord, the first condition. Then we are increasing the CG, keeping the aerodynamic center same. So as you can see over here, our design point is changing every time. So this is our trim angle of attack for the first case, this, and this is for the second case where it is intersecting with the 0. So that is the angle of attack for which our basically center CM is equal to 0. So this is for the third case and this is for the fourth case. And if we make it neutral, basically it will be go at 38% mean aerodynamic chord. So what we need to ensure that CM alpha is less than negative for stability. So all these things are stable, but if we go above this, it is unstable. So this is static margin. Like we have already discussed what is static margin. It is the distance between CG and the neutral point, and how static margin affects stability. The more we have static margin, the more stable the aircraft. We need static margin greater than 0. As you can see over here, for different aircraft, what is the static margin? Cessna 17%, Boeing 7%, Airbus +1 to -2% because it has fly-by-wire systems. So it can go with a lower static margin as well. For fighter aircrafts, we have a very negative static margin. Concorde is a special case which I will discuss later. So what is the minimum acceptable static margin that we need to ensure for the aircraft? So for aft limit that we need to find, like if we are trying to move the CG, basically our aerodynamic center is behind CG. So how far we can take the CG? What is the minimum static margin? So it should remain within the limits of the operating envelope, and if it goes beyond this, then it is unstable, 40% MSE. And forward CG it cannot, so it should be within this range. And that's it. So forward CG limit is based on trimmability, not stability actually. So we need to ensure that the elevator deflection is enough that we can trim the aircraft at particular angle of attack. If it is more than that, if we need more elevator deflection, the aircraft basically we cannot trim the aircraft. That means it will become unstable. So that determines our forward CG limit. So as you can see, if CG is too far forward, the elevator cannot flare it. So runway touchdown will be on the nose wheel. The next is Mech. So it just shows us how increase in basically once we go from transonic region to supersonic region, how our aerodynamic center changes. So initially it is around somewhere around between 25 to 30 mean aerodynamic chord, but as we go through supersonic region, it goes far behind. So that makes it it gives a very big pitch down movement to the aircraft that is known as Mech. And so we need to ensure that in order to ensure that the aircraft is stable at this point as well, we need to basically transfer fuel backward so that we can shift the CG back behind aerodynamic center to make it stable. This is Concorde. It is a very special aircraft. It is one of the only supersonic airliners. And how Concorde used to manage to fly in such a supersonic speed is basically it has a very good basically fuel management system. So as you can see over here, it used to, so as it goes into subsonic to supersonic, it used to the CG changes from this to this by changing the fuel. So it used to transfer the fuel towards the back of the plane where the fuel different fuel tanks are over there. So that is, and we need to ensure that the CG is managed by fuel transfer. This shows like if it is too forward, then it will cause a very high drag, and if it is if it's too aft, then the aircraft will become unstable. To ensure this, it is between this particular corridor. So I'll show you a video how it is done. Okay. So that is center of pressure. It changes with and So this is like the fuel tank configuration and how the fuel is shifted behind to basically change the CG location backwards. Aft, more aft. This is CO here, the tanks. Next, I will look at different aircraft types and how we ensure the operating CG for different aircraft. So this is Cessna 172. It has a 17% mean aerodynamic chord, so it's very stable. So the wing aerodynamic center is behind the CG, as you can see over here. It's a single seater aircraft, and it is very. That is the reason it is used for student pilots. Then this is like the optimal range for a normal Boeing 737. It is somewhere between 33 to 42% of mean aerodynamic chord, the operating CG. So that will give us 5 to 10% of MSE in static margin, and it is certified by FAR 25. So fuel burn will shift the CG forward, but it will remain within these limits. So it ensures that even if fuel is burned, it will ensure that our CG is within these limits. Then this is Airbus A320. It has like very low static margin, but it uses a very advanced fly-by-wire control systems to ensure that even though with relaxed stability, it ensures a minimum trim drag to avoid basically to avoid instability. So as you can see over here, this is A320, and it has 2 to 5%. It will have relaxed stability, and this is A380. It basically has active CG management, just like Concorde. It will transfer the fuel, and as you can see over here, so B737, which basically uses normal, which is high static margin, basically has the most amount of trim drag penalty. Whereas as we go to a more active CG management, we will reduce the trim drag for the aircraft. Then I will look into fighter jets. As you can see over here, this is the curve for static margin and pitch response. So as you can see over here, as we go below, we have fighter jets which have basically where the CG is basically behind neutral point, and the static margin is actually negative. 7% for F-16. X-29 is an extreme example with 35%, minus 35% negative static margin. So CG is at 45% MSE, and neutral point is ahead of it. It is at 38%, as you can see over here. And so static margin is negative 7%. It is naturally unstable. So the reason is that is the reason we actually pilot can not control the aircraft completely, because that is the reason we use FVW FVW control systems, which calculates what is the divergence at every 40th of a second. So 40 hertz is the frequency of calculation. For humans, basically it is like 300 milliseconds is the is the human response time. So that is the reason we need it to ensure that the aircraft is stable. So by design it is unstable. That is the reason. So that trade-off when we get in static margin will give us a better pitch response. So basically it will give us 10% better, faster pitch response than conventional. And that means that even with small angle of attack, we can achieve a higher flight. As you can see over here, these are 3 different fighter aircrafts with different static margin. And so F-16 Typhoon is it's minus 5 to 15%, and this uses FBW digital. So Rafale is minus 2 to 5%. F-18 is plus 1 to 3%, and MiG-29 is conventional is 5%. So we need a fly-by-wire correction system for this kind of aircrafts. And this is another such example. This is Eurofighter Typhoon that I discussed earlier. It has minus 2%. It uses FVW, but this is SR-71 Blackbird. And it has a 6-tank fuel management system. So it basically changes the fuel to change the location of the CG to ensure we are at the minimum trim drag. The other thing is lateral stability, lateral directional stability due to change in CG and AC. So CG and AC doesn't have much, position of CG doesn't have much effect on the lateral or directional stability in the much it has on the longitudinal stability. It is more governed by this particular vertical tail, which is the more important in this particular. The only thing that we need to ensure that if CG is forward of neutral point, then it basically means that and CG is forward of fin aerodynamic center, then it will ensure that the aircraft is stable. And the only way it will come into effect is this: if we have a higher CG, it will ensure that our dihedral effect is coupled and our rolling moment is stable. This is a particular research. It basically instead of like calculating a neutral point using basically normal wind tunnel test, which takes a lot of time. They're trying to calculate the neutral point in flight. So basically, running test flights and then trying to calculate neutral point based on what they have got, and they have 50% lower uncertainty than the conventional wind tunnel methods. And but one critical result of this is that the propeller strips. This is a propeller aircraft, so propeller strip streams basically shifts the neutral point with different power settings. So different throttle will shift the neutral point differently, and that will vary. That will vary the static margin. So thrust will basically vary the static margin. That basically means that our static margin is also coupled with thrust of the aircraft as well. Then these are different limitations that we have taken in this theory. Basically, our theory is a very linear theory, and it assumes small angle of attacks, perturbations. So that is the reason, and the flow is the structure is rigid. There is no aeroelasticity effects, and the flow is completely attached. But in reality, there can be many things. There can be non-linear effects for high angle of attacks. There can be wing tip vortices, and aeroelastic bending as well, and the power effects that I included earlier due to thrust, that can actually cause the static margin, CM, AC, everything to shift by large factors. So that is the reason we need to ensure a safety margin whenever we are designing an aircraft. This is just how we reach first we decide a CM position, then moment arm, pitching moment. Then we need to ensure the stability criteria. From there we get the static margin. And that is how we decide what is the control system we need for the aircraft. And that is comes down to which aircraft we are trying to design. So this is one thing that I want to actually. So primary stability lever actually is our horizontal tail, and increase in tail volume coefficient that will increase our stability. That we can see over here. How we can increase the size of the tail and make the aircraft more stable just by increasing size of the tail. So since our trim angle of attack earlier, I told about like we need to find this particular angle which aircraft will fly at the most point, which is the trim angle of attack. It is basically dependent upon the elevator. So how much our elevator is negative will ensure we can change the lift of our tail, and that will basically help us determine what is the trim angle of attack in the CM alpha curve. Then this is stick fixed and stick free neutral point. So stick fixed is like the elevator is physically locked at a trim position. Whereas stick free is like pilot releases control, elevator floats and trailing edge up. It reduces the tail lift. So a floating elevator will basically move the neutral point forward, and that is basically will shrink our static margin. So that is the reason we need both stick free static margin and stick fixed static margin when when designing an aircraft. Now I will invite my friend Deep to continue this presentation.
Good afternoon, everyone. So I am continuing from the fuel consumption part. So fuel consumption continuously migrates the center of gravity. So as fuel is consumed, so the center of gravity, it tends to shift depending upon where the fuel tanks are, the position of the fuel tanks relative to the aerodynamic center. So this plot actually gives how the CG position changes with respect to time, as including trim tank transfer during if trim tank transfer during cruise happens. So trim tank transfer during cruise actually helps to stabilize the CG position as the flight moves. So now I will come to effect of payload and fuel loading on CG position. So I have just discussed regarding the fuel loading, like as fuel is consumed, the CG position changes, but the effect also stems from how mass is placed inside the airplane. So CG varies with a passenger distribution, cargo placement, fuel quantity, and tank sequence. So as fuel burns, as I've already said, wing tanks deplete. So CG shifts depending upon the placement of the tank. In fact, placement of the wings in this case because it's in the wings, and the placement of passengers or the cargo, it should be within both the forward CG limit, which gives the maximum SM, and the FCG limit, which gives the minimum SM. So if we don't follow these limits, it may lead to uh, catastrophic effects, as it has happened before. So now I will come to how engine thrust placement directly couples with pitch stability. So this equation, in this equation CMT, it's directly related to ZT. ZT is the vertical distance of thrust from the ground. So if ZT increases, that means the engine goes higher. In that case, the CMT increases in the negative direction. So as a result, the stability margin increases. Stability margin increases. So for example, in the high wing ATR 72, so as the engine or the thrust is placed at a higher position, so there is a greater stabilizing nose down effect as compared to the low wing pod at 737, in which the thrust is at a much lower height as compared to the ground. So as a result, there is a destabilizing nose up effect moment. So one case study regarding thrust coupling. So yeah, 737 released its new variant, 737 Max, in which they used a bigger LEAP 1B engine as compared to the CFM engine, which they had used earlier in NG. So CFM engine was a larger engine, so it was moved forward and it was moved higher for ground clearance. Because of the increase in the thrust momentum, so it created a severe nose up pitching moment at high angles of attack. However, as regulatory evasion, so that the properties of the earlier 77 NG are simulated. So Boeing added the MCAS software to simulate the older NG handling, and they didn't include it in their manuals. So, however, due to a single erroneous angle of attack sensor, it triggered unrelenting full nose down trim, which had catastrophic outcomes, leading to two crashes and 346 fatalities in total related to the 737 Max. So now coming to flying wing, a tailless aircraft. So in case of tailless aircraft, as I had already mentioned, the CG range is very low. Like we don't have a lot of CG range here. And in this case, since there is no tail, reflexed airfoil or S-shaped airfoils works as a tail and enables stable trim. So in this case, the stability margin or the static margin, sorry, is not high. So FBW is again essential for CG management and active stability augmentation. And in this case, as has been mentioned numerous times, wing alone must provide both the lift as well as the stability. So coming to canards, so canards have a destabilizing contribution to AC. It brings the AC forward to CG, and the main reason for putting in canards is to increase the agility of the aircraft. So it's used in fighter platforms like Rafale, Typhoon, even in the upcoming Tejas Mark II, and so on. So canards improve agility and direct lift, but it reduces natural stability, as is the case because we want agility. So here I'm giving a comparison of the supersonic transport between Concorde and the next generation boom ovator, which is in design phase. So In case of Concorde as well as in boom overture, there will be obviously Mach tuck because they are moving at supersonic speeds. But in case of the newer boom overture design, the speed is lower. It's the Mach number is lower as compared to Concorde, so it's manageable. And second thing is Concorde didn't have a digital fly-by-wire system which is incorporated in the newer design, so it will make this CG management a bit more manageable and also will enable tighter CMAC tracking. So this is similar to the tailless design. This is the blended wing body. Here also again the advantages are that we get higher lift to drag ratio, so it becomes more efficient. However, the CG range, just like the tailless designs like B2 Bomber, is very narrow. So here also we need fly-by-wire system, just like the tailless design. So now coming to comparative summary between the different types of aircraft. So no single aircraft is optimal in all the stability parameters. Some will be obviously more agile while some will be optimized for more stability. So this table gives the various ways CG management is done and how control is achieved. So just from looking at the graph, the CG management is complex in case of Concorde, but it has higher Mach range stability because it is designed for supersonic flight, while agility is obviously optimized for F-16 and other such fighter aircraft. So these are the different cases for which we have different optimized stability parameters. So he had mentioned about the studies which focus on stability, focus on basically the rigid wings. So in real life, however, wings don't remain rigid. So structural flexibility also has effect on the aerodynamic center. So so there is some wing bending which happens on swept wings, which effectively shifts the aerodynamic center forward under aerodynamic load. For example, in case of Boeing 787, so the wingtip deflects more than 7 meters, which leads to significant AC shift, as you can see from the plot itself. So as a result, the static margin reduces as the wing shifts more at greater air speeds. So the fly-by-wire systems, they basically compensate for this aeroplasticity effects which happens here. So now I will talk more about how active CG management is done through the use of fuel transfer. So in this case, this is the entire flow chart which is used. So there is this max sensor, altitude sensor, and the fuel quantity sensor which gives input to the CG position computer. And CG position computer basically measures the difference between what CG is present right now and how much CG is required using the CG target scheduler. Accordingly, fuel transfer pumps happen, means start, and accordingly it transfers the fuel to the wings or from the tail trim tanks, as you can see in the figure. So the benefit is that it leads to 0.5 to 1% fuel saving per flight. So millions of dollars, euros, everything is saved per year at fleet scale. So what may be the dangers of if we suppose go beyond the CG limitations? So if the cargo is not loaded properly, for example, if the plane becomes too aft heavy or too front heavy or forward heavy, in that case, either if it's front heavy, the CG will move too ahead, and in that case, the trim drag will be too high, and it will, number one, be economically a bit disadvantageous, or it may even lead to like problems while trim. While on the other case, if the cargo is loaded, for example, in this case for the cargo aircraft, if it is too back, the CG will go way beyond the safety limits, and the flight will become unstable. So FBW provides limited protection, but it cannot substitute for proper CG management. So CG management is must. So now coming to trim drag connection, as I've said, so for forward CG, you have greater trim drag the because the tail has to compensate higher for higher down movement, forward movement. So in that case, the trim drag penalty is higher as compared to FCG. So trim drag can represent around 1 to 3% of the total drag, which leads to significant fuel cost. So coming to the economics, so every 1% fuel saving from CG optimization, it leads to some $800,000 per year savings at 2024. Now it's pretty high. It's higher now. It crossed million, I guess, right now. So A320 has this trim tank system which I had discussed. So it saves about 1.5% fuel. So you can just calculate the savings from there. So CG management software, it runs on the modern flight management systems. So this is the plot which gives the CD versus CL. So 5 correlations which define the CG AC stability framework. So forward CG, it will lead to stable aircraft, but if the CG is quite backward, static margin will be less and it will be unstable. So this is the stability margin spectrum plus so this is for all types of aircraft present. So tail is the primary neutral point shifter, and I'd also discussed about the trim tank management. So this is the aircraft design tree. So based on what will be the mission requirements, the target static margin is set, and accordingly different parameters of the airplane design are taken into account. So for example, we have wing sweep, tail sizing, CG management system, and depending upon if natural stability is present, whether FBW is required or not. And there are different certifications also based on the static stability, handling qualities, and so on. So in conclusion, stability margin is quite an important part of aircraft design, and based on what mission the aircraft is designed for, we can have different stability margins. So thank you.
Questions? Do you have any questions, Ranjapa? Yeah.
It stopped the timer again.
It's not being respected.
It's not possible not being respected.
It's universal. It's not one team. Yeah. Go ahead.
What was the question?
How did you create?
Prompt.
I think the question was pretty straightforward. How do the following parameters affect the longitudinal static stability of an aircraft? So it was limited to longitudinal statics, and also I think your subtopic was position of the center of mass relative to the aerodynamic center. So I think very, very clearly defined, not much leeway to play around. So I was really surprised you could have so many slides. I had a few questions to start with, but I think the later slides kind of covered all the answers to those questions as well. But one thing I saw in terms of comparison to your previous presentations to this, usually you do a pretty good job at trying to understand the basics. I think here I could see a little bit of lack of that, especially in the first half of the slides. I want you to go back to your peak performance and then not drop from there. Okay. As always,
Number of slides are too large. I was trying to rush forward, so
Right,
I'm not able to
right.
explain.
Right. Again, it's a common thing that has been happening with all your presentations as well as many others who are using AI is, for example, because your focus was on longitudinal static stability, longitudinal in particular. What you really needed is the plane of symmetry where the static margin is defined. So in many pictures I saw it is the other view, not relevant. And then you're showing the CG and NP somewhere going along the span of the wing and things like that. And what you're having in terms of the content, the text is not kind of correlating with that. At least there are 3 or 4 slides flights like that, where the CG and the neutral point are shown not in the plane of symmetry but out. I mean, it can happen because of the loading and other things, but not to the extent that it is exaggeratedly shown there. What you really wanted to convey was what is happening in the plane. The next thing is in terms of the position of the center of mass, shifting of the fuel from one set of tanks to another is a very common way of doing it because the fuel mass fraction is fairly large. But also in many situations, you could have the cargo initial loading itself because you don't typically request the passengers for their weight data. So you have to work on very rough values, and probably the uncertainty levels are fairly large. But they are very strict at measuring not the cabin baggage, but at least the check-in baggage in terms of the weight. So they have very clear data related to that. So how they load that onto the aircraft, that's another interesting study. I think you briefly touched upon it, but without much data, that could have been a direct addition towards your subtopic in terms of how they do it. Another thing is mid-air refueling. So when you're doing mid-air refueling, how in terms of the consumption of the fuel, in what direction you empty the tanks, in some cases transfer also. When you refuel, how you utilize the various tank locations. These are probably some things that you could give thought. Okay, so you're going to go ahead with your 7th presentation?
No, sir. We'll give the opportunity to other team to second.
You've done that too much. But I want you on Monday to finish all your backlogs, which means 7th and 8th.
Sure.
Okay. Yeah.
Good afternoon, everyone. Our team is Turbulence Squad, and today we are going to present, in context of static margin, how the static stability and itself, the control of the aircraft is can be interpreted in terms of the static margin.
I have. That was mine actually. Okay.
So, team, the Turbulence Squad, myself, garuḍā.
Go ahead.
Yeah. Sir, we have all discussed in very depth like what stability is all about in our previous topic, and how the static margin has been defined across various ways we have been discussed. But the current topic, the current question was basically how this can be linked to the control of the aircraft. So I wanted to have some intuition about how this stability and especially the static margin, which is our topic, how it develops an idea how we can use a controllability or control system to effectively control the stability of the aircraft. So in the previous presentation, when we defined static margin was defined as a parameter. It was, and we discussed in depth and detail that how it can be computed for very simple cases. But remind you of a fact that static margin is not really a parameter for an aircraft. It really varies from point to point at different points in the envelope. So essentially what happens, it depends whether it is in high angle of attack regime, whether it is doing a maneuver. So there are different cases where the static margin can actually change over the aircraft. So there is a range of a static margin which is there for the entire flight envelope for a given aircraft. And as we know, the static margin can also be positive and negative. So if it's positive, then there are naturally restoring forces which tend to bring it back. But what about when it is negative? When it is negative and there is no control system, then yes, the pilot has to do a lot of effort to bring it back because the tendency is not really to come back. So he has to put a lot of effort. But that is not really possible for a human to maintain that kind of a level of control. So that is the reason why the control systems are actually given, that authority to take over the controls and make the aircraft from the regimes where the static margin has become negative and to bring it back to the stable if any disturbance is coming into the picture. So there is a very classic historical example which is basically the saber dance and which happened in the very first variant of the US F100, which was a bomber and it was the first supersonic fighter jet. At low level it could fly, but the problem with this aircraft was this had a very high sweep angle, and due to this high sweep angle, when it landed, it had to land at a very low angle of attack, and obviously we need to have a high sweep angle for the supersonic design. But the problem was in the initial variants, the vertical tail was very small. So when it actually came for landing at a very high angle of attack, so there was a tip stall, and because the tip stall, as I told, the aerodynamic lift actually shifted to the inner, the root of the wing, and that is the reason why the aerodynamic shifted forward, and because of that there was an adverse pitch So that needed an requirement for a control system to stop the aircraft basically getting upside down. But also not only that, if there is a lateral gust which gave a small yaw to the aircraft, so that yaw actually led to coupling of the roll. As we know that because of the yaw there is a coupling of that one. But because of the initially lack of any control system or a smaller vertical tail, this aircraft was very difficult to control from this Dutch roll instability, and it had led to many severe crashes in the initial variants, and thereby many design variants were basically introduced where this vertical tail was made bigger, so that naturally the yaw stability was also introduced. And also in the case when this unstable oscillations grew further and it was beyond the scope of the human controls to bring it back, so the control system was also established. So we can see that how the knowledge of static margin actually helps us to decide whether what is really required in the design. Sometimes it is not really possible for naturally to create such restoring forces, and that calls for the control design. And we have seen now all the modern aircraft, whether it is a fighter or commercial airliners, even the mini cargo airplanes, without control system it is very difficult. And now the control system has really made the life of the pilots to combat such kind of unstable situations in coming in aircraft. And further to this, many case studies and further insights will be given by our teammates.
So hello everyone. So let's see, already we have gone through the static margin before, so I won't take much of time. Basically, static margin is the non-dimensional distance between the center of gravity and the neutral point. And this configuration you see here is a case of a positive static margin, and in case of negative static margin, the aircraft is usually stable, and the stability and unstable was pretty well told by our garuḍā sir. So moving on to the next slide. The slope of the coefficient of Cm upon del alpha is a negative. Why this is negative? We can see when an aircraft experiences a disturbance, and suppose the angle of attack increases, then we need to decrease the angle of attack. For that we need a negative Cm, and for the vice versa, if the angle of attack decreases, then we need to increase the angle of attack to be stable. So Cm is positive. So that is why del Cm upon del alpha is taken as negative. That's all. Now, but Bharat will continue from there.
Hello everyone, my name is Bharat Kumar, and the static margin can be given in terms of mathematically with relating to the pitching moment derivative and lift curve slope. As we can see, the lift curve slope is a positive, and static margin also comes out to be positive for positive stability, and these are directly proportional to the pitching moment derivative. The pitching moment derivative should be negative for positive stability. So we are intentionally giving that minus sign to convert, because the lifting curve slope and static margin are positive. We need negative stability, negative pitching moment. So it is giving the finally it is giving the positive stability for the aircraft. And one more thing, everyone considers like for static stability we only design in a theoretically we only design for wing, but there is one effect, it's called Monk effect. This is because when there is a small angle of attack in any fuselage, it produces a small lifting force at the head of the CG of any fuselage. It is called lifting cylinder. This is because when this lift is produced at ahead of the CG, this will create even destabilizing moment in the fuselage. This again leads to the shifting the neutral point bit ahead, thus reducing the static margin of any fuselage. This will decrease the static stability of fuselage. From now, Somik will continue.
Hello everyone, I'm Shomik. So we have already seen about the static stability concepts, and few of the fundamental concepts have been explained by my teammates. So here I'll be speaking about the location of the horizontal stabilizers and its effect on how it changes the static margin. So here we can see we have the horizontal stabilizer aft of the wing, which is inherently a stabilizable configuration, and this and it determines the size of the horizontal stabilizer directly determines the stability performance of the airplane given by the factor, the tail volume ratio. And as we can see, although the horizontal stabilizer placed aft of the wing gives a better stability performance, but it has to pass through the dirty air of the wing's wake, and as a result the effectiveness is reduced much. And so here we come to the configuration words, the configuration of a canard and an aft tail. For the canard, the lifting surface is ahead of the CG, and in most of the cases it reduces the static margin by bringing this neutral point forward, and often and most of the times it makes it negative also. Whereas in the aft tail configuration, the NP is behind the CG, which is desirable for static stability. But canards, although they are aerodynamically efficient, they require large control surfaces and like intense engineering for the understanding their aerodynamics and controls. So basically, where to put the two surfaces and make the configuration well, that's a trade-off between the passive stability and the control actions that the engineers need to do. So moving on to my next teammates.
Yeah, I wanted to add one point here.
Please, can you use the mic?
I mean, putting canard is a very classic example where sometimes it is, the CG with the weight management is not, it is going back, and the configuration had to be made unstable. But because of some issue in the design, sometimes canard has to be put so that the inherent unstable design needs to be maintained. But because of that, so it is, sometimes it's not really aerodynamic requirement, but sometimes it is a requirement from controls also to put the canard in the forward.
Yeah, so add with the other factors like the propulsion factor. When we are taking a takeoff, so at that time the nose will pitch up. Because of nose will pitch up, by configuration that the lower airfoil will generate a higher impose to a higher angle of attack, and the upper will be in a lower angle of attack, which leads to the upper thrust force at the propeller nose. So it will shift the neutral point towards the nose, which leads to destabilizing the effect. The range is not much, like it's in a range of 1 to 4%. So it will not contribute that much instability, but it is the one of the factors that will contribute to the instability of the aircraft. The second one is the mark shift. As we already know that in 1950 they didn't know that in a transonic region the CP is as the Mach number is increasing at above 0.8 Mach number, they are experiencing the shock due to the shock and the wave drag. Your elevator is not that much have a control ability to control the aircraft, because due to that wave drag, it's already blanket out that elevator and the rudder part. The second one is why the center of pressure is shift to aft at around C/2, because at a lower Mach number, let's say in the subsonic region, where the information of the information flow is ahead of the sound of the speed. That's why we will get this type of CP graph, and from this graph we know that the center is on the C/4. But as we go on Mach number at Mach 1, where the aircraft velocity is so much ahead of the sound speed that information is not carried out ahead of the air, due to which the the pressure distribution is distributed along the airfoil more or less in in the equal way. That's why the center of that CP is C by 2. And also we can see from that equation that from this equation we can also find the similar effect that as the Mach number is increasing, the CP distribution is distribute out equally. But what's the effect if it's distribute equally? So due to which it will because we have designed an aircraft such a way that it's in static its neutral point is at some point for subsonic region, as will go up to the supersonic region. Due to the shift of the center of pressure from C by 2 to C by 4, the neutral points go aft of the aircraft, due to which by nature aircraft will nose down. And also because they have, if it's operating in a transonic region, due to the elevator have that doesn't have that much authority, due to which when the pilot tries to pitch up the aircraft, it will not able to do that. So what are the solution for that? That they are using the whole elevator to pitch down, so that we can also use the elevator area itself to pitch up, and also the fly-by-wire method that the computer itself is generating. So in a 1/4 time calculation that will control the aircraft itself. Now move forward to we'll talk by Gaurav.
Here I will be talking about the effect of flexible wing to static margin. So during high speed flight, so lift will go up because lift is proportional to velocity square. So because of high lift, there will be high bending moment to the flexible wing. So because of that, the wing will bend more. And if there is a positive sweep angle to the wing, so what will happen? Because of positive sweep angle, so because of positive sweep angle, so because of the bending moment, so what will happen? There will be a twisting moment. So because of the twist, the trailing edge will go up compared to the leading edge, and because of that, there will be a decrement in angle of attack at the wing tip region. And because of that, the lift will go down, and this is known as lift dumping. And as the wing is having a positive sweep angle, so the tip is actually located down a little bit downward direction with compared to the root region. So because of that, if we calculate the point of action of the lift force, so we can find that the lift is actually moving in upward in forward direction. So because of that, the neutral point will actually move to CG, and because of that, the static margin will go down and the stability will go down. And next, I will be talking about relaxed static stability. So basically, the neutral point is kept intentionally to forward to CG in fighter aircraft. So because of that, the static margin becomes negative, and because of that, the aircraft becomes unstable. And the aircraft can have two benefits of that. So during motion with positive pitch angle, so what will happen as the aircraft is unstable, so it won't come back to zero pitch position. So because of that, the aircraft is able to generate lift from the tail. And as we know that the tail surface is very less compared to the wing surface area. So because of that, the induced drag will be very less, because that is proportional to the surface area of the tail or the wing, whatever. And also because of that, the trim drag will be the induced drag will be very less. And also as the aircraft is unstable, so it will give very quick response to control inputs. And next, Neerav will continue.
Good afternoon, everyone. Myself, Neerav. So, we know that traditionally the aircrafts are inherently stable, but when we introduce the relaxed static stability concept, RSS, the aircrafts become inherently unstable. Why? Because the static margin changes its sign, so there is no more restoring force for a positive or any gust in the pitching direction. So there is no restoring force inherently. So how do we solve this problem? By introducing the relaxed static stability is we introduce fly-by-wire technology instead of using mechanical linkages in order to reduce the reaction time of a human pilot, which is generally of the order of around 250 milliseconds. So we introduce a digital feedback loop whose reaction time is approximately 10 milliseconds or so. So what it does is assigns some extent of control to the computer itself. So it reads the at the time on spontaneous data for the angle of attack and the pitching rate, and it updates the pilot input by doing minor corrections in order to put the aircraft in its position, because it is inherently unstable. So by making the aircraft inherently unstable, now the aircraft has no restriction on kind of going up. So it so happens that in some cases it can go up and up, and at a certain angle of attack it gets stuck there. Because there is no restoring moment inherently, it can get stuck after a certain angle of attack, and then the normal control surface, since at this high angle of attack the tails are generally in a region of turbulent wake of the wing, so they are not controllable at all, or let's say they are not effective at all. So we cannot restore the aircraft by traditional methods, or by traditionally controlling the tails by any method. We cannot control that after our aircraft reaches at that stage. So what we need is to prevent that stage completely. So for that, modern aircrafts use modern control laws, which were first introduced in this paper, which inherently stops the aircraft and prevents at any cost to reach in such state, because that is not recoverable by any means, any physical means. It is not recoverable. So yeah, that's what this technology does, and every modern aircraft which uses the RSS method uses this technology in order to prevent the stage. And why we use this? Because by using RSS we can get highly maneuverable aircrafts, and we can get maneuverability at very low cost. So yeah, next my fellow cadet Adarsh will continue.
Good afternoon. As we all know that during the movement of aircraft, the neutral point is shifted because of the forces experienced on the wing due to wings flexibility. But we can also control that flexibility by aeroelastic tailoring. By aligning composite piles asymmetrically, we force the wing to twist beneficially under load. Due to this, we can control the neutral point with material science also. Now we know that setting margin depends on CG, position of CG and neutral point. When the aircraft flies, the fuel burns, which results in change in the position of CG, and neutral point also changes as the airspeed Mach number increases, or due to G load on the wing. So this is a 3D graph of all possible altitude and Mach number. Here this green color tube is the safe zone for static margin. Thank you.
The previous slide, two of the axis legends were the same.
Yes, sir.
Altitude V, altitude Y, altitude Y. What?
I think sir, that is a projection, I think. Because there are 4 variables here, sir.
It's just a projection. It's just a projecting in 3D.
Projecting what? Why is it repeating? It's not supposed to be repeating this. You have altitude Y on the vertical axis as well as the one coming out of the board. Both are altitude Y.
Yeah, the vertical part, it's mistake. There is no altitude. It's just
What is it?
It's just a project.
Projection of
in this 3D envelope. That's if you want to visualize the reaction,
whenever you get outputs like this which don't make sense, you have to give more prompts to find out what it's trying to convey, right? Whatever the AI tool is conveying, you have to try to find out. It's like otherwise it doesn't make sense.
That is what the projection is telling. That altitude y is not the label actually. That's wrong with them.
Okay.
But what you see as a 3D, the points, that is set of this collection of points, which shows you that as the aircraft flies, what is the regime where that neutral point shift is happening due to different conditions. As we said that it is just not a number. It depends on many things.
Sure.
So that thing shows that how the entry is shifting for a given combination of the flight values.
Right, I understand the point qualitatively, but
That might be by mistake that that's a straight there label. So the whole idea was to show that if we take all the factors, the structural flexibility, the design, for example, if you have a canard or by design itself, they're shifting the NP.
Yeah.
So how the value of static margin can be utilized can be utilized for the control and doing much more things in the fighter, and also if when it is not possible for a pilot, how it can be utilized to design a control system which keeps the aircraft stable and keep on flying.
no, I really appreciate you having looked at some of the most modern technologies and ways in which the static margin can be played around with for different requirements of the latest generation fighters, etc. Also, I like the slide designs which are kind of compact, but don't mistake me that I'm just pointing out this particular slide because it just happened to be previous to the thank you slide. But these kinds of issues were there with many other slides as well. I just want you guys to put a little more attention to the outputs of AI tools. Many times it's very useful and gives in a very short, compact way, very easy to decipher certain information, but at the same time it gives all kinds of spurious things. Try to correct that and put something that is more meaningful. That's what I request you from your future presentations. Going to a very basic question, these three quantities like neutral point, aerodynamic center of, let's say, the wing, of the tail, etc., center of pressure also, many a times I found it kind of interchangeably used. Yes, there are conditions under which they can coincide. Again, in that also you have to be a little careful in taking care of that. I just want you to answer the true or false. Can the neutral point be thought of as the aerodynamic center of the entire aircraft?
Yes, true.
Yeah.
If you look at a body over which there's an airflow, so definitely we'll have a center pressure for the entire pressure distribution, and about that center pressure we can take all our moments, and that is what is interesting. That itself can change at different points in the language. So yes, it is actually, and that is the reason why we need to design according to this variation in the location of NP or the static margin values.
While designing, we have don't just consider like a wing or tail differently. By just taking a static margin also, we can define a whole aircraft for any regime.
Many design configurations which can give the same static margin. So there are other things which determine that. Thank you. Who is ready next?
Good afternoon, everybody. We are Team Right Wing, and we are here to answer the question: what effects do the following have on the static stability of an aircraft? And in that, we are going to discuss the contribution of tail and wing. Here are our teammates, and I'm Karthik. So, just looking back at the definition of static stability, it is the initial tendency of a body to return to its original equilibrium position after facing a disturbance. The most common example that we've seen and heard throughout is a ball in a bowl. For an aircraft in static equilibrium, it is defined in such a way that the sum of all forces or moments, defined as Fx, Fy, Fz and Mx, My, Mz, must be 0. Now, for directional static stability, vertical stabilizer is what inherently achieves it. And for roll static stability, we require a dihedral. But the main concern here is the longitudinal static stability. It is of the most concern because it is very sensitive to the CG location, which in turn depends largely on the wing. Now, looking at the governing equation of longitudinal static stability, it is defined in terms of My, that is the pitching moment coefficient about the y-axis. Writing in terms of cm, we get m by q s c bar. We've seen it before. We've seen these graphs also before. Just to summarize, given a disturbance from its equilibrium position for a particular, for aircraft 1 which has a positive slope, it tends to become unstable as the pitching, as there is additional pitching moment. Conversely, for aircraft 2, it tends to be stable as it returns back to its initial position. Now, hence we get the condition for static equilibrium, static stability, that is dcm by dcl is less than 0. From the second graph, we see that the equilibrium lift coefficient must also exist. That the graph should intersect the x-axis, which gives rise to cm naught greater than 0 condition for static stability. Now, the principal contributors to this pitching moment are effectively the wing and the horizontal stabilizer. Just looking at tailless aircrafts, and we see that the pitching moment coefficient about the aerodynamic center is significant. That is defined as MAC. Now, in that image, neglecting the contribution of the tail and only considering the wing, we get this moment equation written as MAC about the aerodynamic center and lift acting at a distance xCG minus xAC from the CG. Now, non-dimensionalizing it with Q, S and C, we get in terms of coefficients Cm and CMAC and CLW. Now, CMAC is independent of angle of attack, which means it's also independent of CL. Now, getting the slope again, dcm by dcl, we get that equation xCG minus xAC by c bar, which again, going back to the condition, stability condition, we require dcm by dcl less than 0. That means xCG must be less than xAC, CG ahead of AC. For unstability, it is CG behind AC. Now, this is governed by the wing characteristics. Hence, we can say that the wing is a major contributor to the longitudinal static stability.
Hello everyone, I am Anjali Singh. So let's talk about contribution of tail. For static stability, the dou cm by dou cl should be negative, and for stable condition, it should be unstable condition, it should be positive. Why negative and why positive? To understand this point, we'll considering two aircrafts, one with positive slope, that aircraft 1, and one is negative slope with aircraft 2. Okay, let us consider that there is some disturbance due to which there is a pitching up movement, like disturbance, like is there any air gust. So for if we talk about aircraft 1, if there is any disturbance which cause its pitching movement, which will result in high angle, more angle of attack, increase in angle of attack, which ultimately increase in CL. So increasing CL will ultimately more increase its angle of attack, and this will continue, which results in the unstable aircraft performance. If that dou cm by dou cl is negative, means if we consider the aircraft 2 which is negative slope, if it is facing the same disturbance like for air guts, if having its pitched up movement, but it has negative slope, so if angle of attack increases, which increase in CL, but because of negative slope, that pitching movement will be nose down, which will stabilize our aircraft. How we are getting this relationship is, you can see in the picture, we are just summing the moments. For non-dimensionalizing the equation, we are dividing with the QS and C quantity. Then we get that relationship between dou cm by dou cl. The second term is which mostly represent the contribution of horizontal tail to the static stability of the aircraft. So all the quantities here are positive. So this term is negative. Negative means it will contribute to the stability of an aircraft. But that stability in which condition? When this condition, that point, first quantity is negative, means that aircraft should, aerodynamic center is ahead of CG, it will be has less, so overall quantity will be positive, which will result in instability. But if it is behind that aerodynamic center distance will be more, and the both quantities will be negative, ultimately results in negative slope, which results in a stable aircraft. Okay, my teammates will continue.
Good afternoon, everyone. I am Tarishi. I'll be talking about the static longitudinal stability, specifically the stick fixed condition. So what is stick fixed? Stick fixed is the controls are rigid. That means they have no effect of wind on them. They are not free to float due to wind. This is the pitching moment equation, which this is the total pitching moment coefficient pitching moment coefficient at zero lift and the slope of the CMCL curve. This is the lift coefficient of wing, and that is elevator effectiveness, that term, and it is defined as that. If we look at that, as the CG moves forward from the graph, as the distance increased, you require a larger amount of moment to balance the unbalanced force. So you need a higher elevator deflection to balance that. And also by changing the elevator deflection, the slope of the CMCL curve does not change. So the static stability of an aircraft is the same, but you can change the trim angle according to the pilot requirements. If you want to fly at a higher speed or a lower speed. Thank you.
Good afternoon, everyone. I am Vaishnavi. So now coming to stick-free static stability. So what happens when the elevator is free to float? So it is applied when the elevator is allowed to float freely under aerodynamic pressure. It gains its own equilibrium. So the air flowing over the tail creates a moment around the hinge. The free elevator will mechanically rotate until it finds a position where the hinge moment is zero. So when there is a disturbance, the angle of attack of the aircraft changes. So the elevator is free to float. It will gain an equilibrium position. So it will deflect. So due to this deflection, there will be a decrease in lift, so which will create a pitch up moment, so which is destabilizing in nature. Now coming to the hinge moment. The hinge moment is driven by two factors. One is change in angle of attack, which is CH alpha. This is the floating tendency, and the next one is the change in deflection. This is CH delta, the restoring tendency. So the deflection of the free floating elevator is defined as minus CH alpha by CH delta into alpha t, that is angle of attack of the tail. Now coming to the factor F, how much is the loss as compared to the stick fixed one. So the factor F is defined as 1 minus change in hinge moment. Here 1 minus CH alpha by CH delta into CL delta by CL alpha. This term CL delta by CL alpha is defined by tau E, which is the airfoil tail control effectiveness. The contribution of the tail to stability is reduced when the stick is free. So the factor F, we can say that it is obviously less than 1. So when we are calculating the stick free lift coefficient, the lift coefficient is multiplied with the factor F, which is less than the stick fixed lift coefficient. This reduction means the tail provide less restoring force per degree of pitch than calculated for a rigid aircraft. So CL for free elevator is less than the fixed elevator. Because the stick free tail is less effective, the entire aircraft's aerodynamic center shifts forward. Now we'll see stick free neutral point. So there is a small flap attached to the trailing edge of the elevator, which we call it as trim tab. So when deflected, the trim tabs have negligible effect on lift and drag, but produce a moment about the hinge line, which can offset the elevator hinge moment. We have seen the hinge moment coefficient is defined as this. In this equation, the CH naught is 0 as we are considering symmetric trails. From this equation, when we equate it to 0 to make the hinge coefficient 0, we'll get the elevator deflection as given in that equation, minus CH alpha into alpha h plus CH delta t into delta t. Alpha h is the angle of attack of the horizontal tail, and delta t is the deflection of the trim tab, and delta is the deflection of the elevator. The angle at which the elevator floats depends on the angle of attack. If alpha changes, then delta E will change for the given tab setting. Coefficient of moment with respect to alpha, that is dCm by d alpha, is given with this equation. Here the highlighted part, that is the 1 minus tau e ch alpha by ch delta e. This term reduces the horizontal tail effectiveness. In addition, the aerodynamic center or neutral point of the aircraft becomes xac dash. Through this equation, we can calculate the neutral point. And when we compare it with the stick fixed neutral point, it is less than the stick fixed neutral point. That is, it shifts forward. So because it shifts forwards, the static stability is reduced. Moving forward.
Good afternoon, everyone. I am Navya. Today I will explain you about the static directional stability. So coming to the definition point of view, static directional stability represents that the initial tendency of your body to come back to its original position or equilibrium position when there is a disturbance in yaw. That is called as the static directional stability. So what does it mean by the disturbance in yaw is nothing but the disturbance in yaw can happen because of the wind or gust effects. Now before proceeding further, let me explain you what is happening across the axis and all. We can see this. So this x-axis is called as the longitudinal axis, z-axis is called as the directional axis, and y-axis is called as the lateral axis. So the movement acting about the z-axis is called as the yawing moment. Now the component which corresponds to the yawing moment is nothing but the tail. That is the vertical stabilizer, vertical tail. So vertical stabilizer will be contributing to the yawing moment n. Now we will see the sign convention. So when the right wing is back, it corresponds to the positive yawing moment. When the left wing is back, negative yawing moment. You can see here, if this is the wing which is at neutral position, if right wing going back represents like this. When the right wing is back, n will be positive. If the right wing is wing is left side direction, then the yawing moment will be negative. Now I will explain you about the side slip angle. You can see here an aircraft which is moving with the velocity v infinity. FRL represents the fuselage reference line. Now whenever there is a wind or gust, let us consider that the wind direction is in this direction. VW is the wind direction. Now we will be inducing a relative velocity. The angle between the V relative and this FRL line is called as beta. Beta is nothing but the side slip angle. Now, when beta was equal to 0, the aircraft is at this position. There is no yaw. That is said to be the equilibrium state. Now, when beta is having a finite value, then these two cases will be corresponding. We will see. In this case, okay. Now, to bring it back, the aircraft to the equilibrium state, we have to apply a restoring moment. The restoring moment applied to bring it back to the equilibrium state is called as the weathercock stability. Now, this explains the derivation. You can see this figure here. When the pitching moment, whenever there is a relative velocity, the beta is induced, like there is a beta. To make beta equal to 0, we have to turn the aircraft. To turn the aircraft, we are getting a case called right wing going back. In this case, we are having the positive pitching moment from, yawing moment. From here, we can say that for positive beta, we are having positive yawing moment. From here, I can derive a conclusion that dCn by d beta is greater than 0. So this is the condition for directional stability. So the movement required to bring beta equal to 0 is called as the restoring moment. Now we can see here, these are the figures which will explain you, which I drawn on the board, this will explain you. Now I'll explain you the derivation. Now, to make beta equal to 0, we have to turn the aircraft. To turn the aircraft, we have to apply the force in the y direction. We have to apply the force in the y direction. That force Fy is equal to half rho v square. Yeah, the force Fy is equal to half rho v square Sy Cy. So this v corresponds to the vertical tail and y is corresponding to the area and c is corresponding to the chord length along the y axis. Now we can see that. Now we know that the yawing moment will be equal to force into the perpendicular distance. From the diagram, we can see what is the perpendicular distance. This is the perpendicular distance. The force into perpendicular distance can generate the yawing moment about the directional axis. Now when we substitute the things and we simplify, we will arrive to the Cn is equal to eta Vt into Vv into Cy beta plus d sigma by d beta into beta. I'll explain you the term called beta is the side wash. When there is a relative velocity acting, the aircraft is turning like this, right? When the aircraft is turning, there will be vortices induced. These induced vortices are called as the side wash, which is denoted by sigma. That is here, it is a function of beta as well, we represent it. So this is the final expression for dCn by d beta. This has to be positive for static directional stability. Now we'll see what are the other factors that are contributing to the directional stability. One is the vertical tail size. If we add fins like dorsal and ventral fins, we can increase the area. By increasing the vertical tail area, we can also increase the static directional stability. Next one, fuselage shape. By choosing the long deep fuselage, we can improve the stability. Next one, wing sweep. By using the swept back wing, we can generally increases the directional stability. Now engine placement. Engine far from center line influences the yaw stability. So this is how we can improve the directional stability by changing some component parameters, and that is the expression which will be contributing to the directional static stability. Yeah, thank you. That's it from my side.
I'm Anjali VV. I'm going to talk about lateral static stability. So if we consider a flight in steady and level flight, as the image seen over there, a small gust will perturb the aircraft. Suppose it will perturb the aircraft, making the left wing fall down. So here we see that since lift is equal to weight, and when we resolve the components of lift and weight, there will be a side force F that is generated, and the aircraft will accelerate towards the left. So this is known as the side slip. Now, since the both wings lie on the same plane, the side slip velocity Vs will see the wings at the same angle. So the same amount of lift will be produced in both the wings, and hence there will be no restoring movement towards the other side. That is why we need the wing dihedral. When wing dihedral is introduced, that is the wings are pushed to an angle gamma, capital gamma. Here, when the velocity Vs is introduced, there will the both wings will be at a different angle from each other. That is, the left wing will see an angle of theta 1 and right wing will see an angle of theta 2. And since they are at a different angle, there will be a lift imbalance in both wings, and hence a restoring moment is produced. So we see that the effect of wing dihedral is stabilizing and directly proportional to gamma in a physical way. And we see also, as Navya mentioned, about the side slip angle. Another point to add is a positive side slip angle will produce a negative rolling moment, as seen on the graph there, for stability. Now mathematically, when we are considering the dihedral effect, we have the change in angle of attack as normal velocity by forward velocity, and the side slip angle tan beta is given as the expression tan beta, and for small beta it will be beta is equal to V by U. And when we are substituting the expression for Vn in the change of angle of attack, we get that V sine gamma divided by U is equal to beta into sine gamma, and since gamma is a small angle, we can approximate it as gamma itself. So dihedral is almost like the easiest parameter to adjust in that design process to tune the aircraft degree of stability to a very reasonable level. So that is all for our presentation. Thank you.
Okay. So Karthik, when you're presenting the contributions of the tail, was that you?
No, sir. Contribution of wing.
Who presented the contribution of tail? Yeah. Anjali sir. Okay. When you're looking at the contribution of the tail, you had this factor eta t. What is the typical value of that, and how can you increase it?
The tail efficiency.
Can you go to that slide?
Which one? What is this?
Yeah.
It's typical 0.8 to 1.2. To increase that, I don't know, what should I do? Increase the span area of increasing
Move the
span area.
camera to left and right. You have that. Yeah.
By increasing dynamic pressure, we can increase the NT, and typical its value is 0.8 to 1.
See, some of the things have come out of that equation, right? Just see where that eta t entered into the derivation.
QT by QW. Sir, QT by QW is replaced by.
Okay. So how do you increase that? Because you want it to be large or small? Huh?
More.
Small.
More.
More. Okay. Why? Anybody else can answer, yeah.
It is the restoring force, right? So we need it to be more.
Okay. Okay. So what are the ways of increasing it?
It's like dynamic pressure of tail to that.
Yeah. Why are they different, first of all, and how can you try to increase that? Yeah, sure. Yeah.
The velocity faced by the tail comes from the resultant velocity after it goes through the wing. It will obviously be different than the tail faces.
Correct. Yeah.
That depends. That ends up with half rho v square. That changes that. Hence QT changes. The way we can increase that velocity is that.
The reason why it is decreasing is because it's in the wake of the wing. So where exactly you put the tail, horizontal tail, will kind of affect, right? Okay. I also liked a lot that Navya and Anjali VV, you presented on static directional stability and static lateral stability, right? Usually these two are coupled. What are the assumptions involved for you to bifurcate this and look at it separately?
Very small angle of attack.
Okay.
At very small angle of attack, there will be
Only angle of attack, or because other angles are involved here?
At the same time, we can consider side slip angle also to be very less. Like if it is the velocity is acting more, the vertices will also be more, which can also cause the couple rolling movement. So to maintain a low angle of attack and maintaining the side wash to be less, so that makes to decouple.
Okay. Want to add anything to that?
The dihedral angle should also be almost. Dihedral angle should not be.
Okay. Okay. Okay, fine. Anybody else have any questions for right wing?
Okay. Hello everyone, we are Team Blackbird and we are here to talk about how effect of fluid consumption on static stability on an aircraft. First, I am Bala and I will give an overview of the basic things we have already know. Like static stability is the ability of an body to return to its original position after disturbances occur. It can be given as like positive static stability where it will come back after the original position, and neutral static stability is the one where if disturbances occur, the new position will be the new equilibrium position, and negative position the system will not come back and will keep on getting gone. And these are as in like we know center of gravity is the point where the weight entire weight of the aircraft is supposed to act, and neutral point is the point where the pitch cm it does not depends on the pitch of the aircraft. So and static margin is the measure of longitudinal stability in an aircraft. It is the distance between the neutral point and the CG divided by the mean aerodynamic chord. Also, static margin is the negative of the dCm by d alpha, which is the indicator of the stability of an aircraft. So, if dCm by d alpha is negative, the aircraft is said to be a stable aircraft. Now, as we know that as fuel is consumed, the weight of the aircraft will change, and as a result, the CG location will change. But if the CG is like changed to forward of the forward location, we can see that the static margin is become positive, and as a dCm by d alpha will become more negative, by which you can say the aircraft will become more stable. And similarly, if the CG goes to aft location of the wing, due to fuel compression, the DCM d alpha will become positive, and the stability will be less stable than the normal case. So we can see from the gas graph or the forward location, this is for the if the CG is in the neutral, and these are for the aft location of the in the aft location of aircraft. Now Elil will continue and further explain about the system.
So, good afternoon, sir. I'm Edil. Thanks for the introduction, Bala. Our topic for the afternoon is how fuel consumption affects the static stability of an aircraft. This topic can be further classified into lateral unbalance and as well as longitudinal unbalance. I'm going to talk about the lateral unbalance. Though lateral unbalance is not of the primary concern, but still it is to be taken care of in order to maintain the stability. So consider this pen as a 1 meter long stick. Now I hang 2 liters of water bottle on either side of the pen, and I hold this pen at the CG of the location. So I drain 1 liter of water from only one side. Now the CG is not at the same location as it was previously. Now the CG has shifted to location towards the heavier side. So holding at the previous CG location, I cannot say that this is in equilibrium. So I have to either hold it at the point where the now new CG is located, or else I have to counterbalance this moment by some effect. So this is what we call as lateral imbalance when it happens in an aircraft. So lateral imbalance or lateral asymmetry in aircraft occurs when the weight is unevenly distributed between the left and the right side, causing an uninterrupted rolling, which also increases the drag due to constant corrective aileron or trim inputs. So this is caused due to the engine is supplied from either only one tank, causing an empty case in one side and the full case in another side. So this causes an additional weight. This tends to roll the aircraft to one side. So in order to mitigate the effects of these problems, it is always important to trace the fuel supply of an aircraft. So the supply of fuel in an aircraft varies from aircraft to aircraft. So this is in like a Cessna 172 or Cessna 162 aircraft, which is a high wing fed by a gravity feed system. In this, the fuel selector valves plays a major role. This both condition refers to the fuel is supplied to the engine from both the tanks, or left or right corresponds to either supply from only one tank. So this supply from only one tank causes this imbalance. In order to maintain the lateral, in order to mitigate the lateral imbalance, the pilot used to always fly the aircraft at the when the selector valve is pointing towards the both. So this causes equal supply to the engine from both the tanks. So in case of a bigger commercial aircraft like a A380, there are tanks which are located at several locations. Like the center tank is located in the fuselage, whereas the outer tank and the inner tank are located in the wing. In some large aircraft, there is a tank located in the empennage of an aircraft as well. So in order to mitigate this lateral imbalance, a sequence is followed in which the fuel is first trapped from the central tank in the fuselage, followed by the inner tank of the wing and the mid tank, as well as then the outer tank. So this sequence helps the aircraft in providing the wing with some stability and rigidity. So this is typical layout of how the fuel is supplied. So these are the main pumps, booster pumps in each tanks, which supply the fuel to each engines. Generally, the left wing usually drinks fuels from only the left wing, and same followed in the right wing as well. So this is a typical layout of an F-16 where the tanks are located. So in an F-16, apart from the conventional type, the F-16 can carry fuel in additional tanks, which are the jettisonable external fuel tanks. These tanks, after the fuel is consumed from it, they are jettisoned from the tank, so to provide more maneuverability. So these are the locations where the fuel is stored for an F-16 aircraft. So some fuel tank configurations are conformal fuel tanks, which are these fuel tanks which are not jettisonable, but the external drop tanks which are once used, they are jettisoned from the aircraft, further altering, since this external drop tank is along the longitudinal axis, it does not alter the CG much. So aerial refueling also alters this CG when this is a B2 bomber. So while flying, if the bomber is starving for fuel, another aircraft gives the fuel to it through aerial refueling. This might also change the location of CG.
So now I'll be explaining about the three cases, which is the three locations of the fuel tank and how does it affect the longitudinal stability of the aircraft. So let's consider a case A where the fuel tank is placed near the CG of an aircraft, that is in the main wings. This is an example for this in commercial aircrafts is Boeing 737. So as far as CG movement is concerned, we can say that this as the fuel burns, the CG shift is minimal. As the moment is about the CG is also minimal, so the CG shift is minimal, and the stability margin remains almost constant. The aircraft does become lighter, but as a whole, the stability stability and the maneuverability doesn't change much. So next in case B, like Errol said, like Airbus A340 has a trim tank. So in that case, as the fuel is burnt, CG moves forward, and due to this, we know that forward CG increases the stability margin, and that way the stability of the aircraft is increased. So we can say that regarding the maneuverability, the aircraft was more maneuverable earlier in the flight rather than later in the flight. Regarding the performance, due to movement towards the early cruise, like we say, as the CG moves forward, the early cruise is more efficient, whereas later, due to the forward CG, there is higher drag, which reduces the performance. So the third case and the last case is the fuel stored in the forward of the CG, and as the fuel is burned, the CG moves aft, and this decreases the stability, but it also increases the maneuverability. However, as the aft CG crosses the neutral point, it causes instability, and thereby it is not used in commercial aircraft. It's used in very early fighter aircrafts like Cessna 210, and yeah, the performance, it also has a reduced trim drag due to aft CG in the later parts of the flight.
So I'll be talking about effect of static margin on fuel consumption in a very brief, since we have already covered in performance of how the static margin affect the performance. So we know that if my static margin is more, the restoring moment will be high, and I have to deflect my elevator more, so that if my elevator deflection is high, my trim drag will increase. When the drag increase, my fuel consumption will also increase. So that I can say that if my static margin is more, my fuel consumption is also more. So now I'll be all these results are taken from the reference paper, which is under the title of study on change of aircraft center of gravity due to the fuel consumption. So in this paper, they have considered a three configuration, for a single tank and dual symmetric and dual asymmetric tank for a different and the constant fuel flow rate. So the point A corresponds to the structural CG, and point B corresponds to the fuel CG, and the point C corresponds to the aircraft CG. So during a takeoff, the point B and point C will be coincide, which will be the maximum distance, and the assumption is that the structural mass doesn't change. So it might be trivial in the case of an passenger aircraft, but in the case of fighter aircraft, when we drop a bomb or any cargo, the structural CG will change. So here they are assuming that the structural CG is constant, and this is the mass of fuel at any time instant. This is the mass of the fuel at initial time. So G corresponds to the fuel flow rate, and time T corresponds to time. So from basic equation, you can get the equation for XCG. This will be the equation of XCG. So for a single fuel tank system, they consider the case of an aircraft Eagle 500, which has zero fuel mass of an 840 kgs, and its fuel mass is 235 and fuel consumption rate is 43 kilograms per hour. So if you look at this graph, like if as the time increases, my CG starts to move in a one direction, which is very trivial. Now, if we consider the dual symmetric tank, if I have a tank at the equidistance from the axis, B1, B2 are the two different fuel tanks. So this will be the equation for location XCG and YCG, Y and X coordinate of CG position. So even if you look in this graph also, it is this graph is plotted for Boeing 737-200 with the data are presented here. With fuel consumption rate is 1325 kgs per hour. So even in this case, the CG is shifting in an unidirectional sense. Since there won't be any, since the mass flow rate is also constant and also my position is like symmetric, so the CG is moving towards the point A, which is a structural CG. So now if we consider an asymmetric tank, which the distance, this corresponds to point A. Now point B. Oh, I'm sorry. Like this plot is for the different fuel consumption, and the initial plot is for the same fuel consumption. So if I consider the different fuel consumption, which means either G1 is higher than the G2, in that case, you notice there is a point of inflection that occurs at the same time in both X and Y axis plot has the same inflection point at the same time. So this point is referred in the reference like since the fuel flow consumption is higher in one fuel tank compared to the other, there is a complete drain of fuel in one tank, and after the inflection point, the entire fuel supply is from a single tank to the engine. So that's why it causes an inflection point. So now if you look at an asymmetric configuration, which I try to draw here, this B1 and B2 are the location of fuel tank. So if you look in a practical sense that if there isn't any defect in the one fuel tank, we carry more fuel in one side of the tank and the less fuel in the other side of the tank. Even in this case, though we have a constant fuel flow rate in the case, but we'll get an inflection point over here, as like the previous case. So this is this graph is plot for Douglas FA-18A aircraft. So even if we have an actual aircraft, we have a trim tank systems and also onboard cargo management, cargo operation systems, so that I have to correctly choose a CG location so that I can reduce my fuel consumption, which also increases my range. So further case study will be explained by Misha.
Hello, I am Vishal and I will be explaining the case studies to understand the stability challenges from fuel consumption. First, let's look at the Concorde aircraft, and the figure on the right shows the tank distribution for the Concorde aircraft. And as you can see, the majority of the fuel has been stored on the aft side of the wing. As the fuel is consumed, the CG will shift forward during the cruise phase. And the one incident that's related to this was 1949, and due to a malfunction in fuel management system, there was an uneven burn between the fuel on the right wing and the left wing, which caused a lateral imbalance, and it was rectified using manual cross feeding, which is just feeding the fuel from one side of the wing to another. And this case is the Airbus A380, and Airbus EC80 has a massive fuel capacity. It carries around 320 lakh of fuels in 11 tank across, as shown in the figure. And during its cruise phase, the CG will software by a minor amount, like 4 to 5%. It increases the stability, but it reduces the stall speed. And during 2007 certification test, due to improper fuel transfer between inner and outer tank, there was an uncommanded roll. Like in the earlier case, there was a lateral instability. There was a 2-degree uncommanded roll. This was rectified by updates from fuel control and monitoring computer. The last final case is the Air Transat incident at 2001. The figure on the right shows its tank configuration. On August 24, 2001, the Air Transat suffered a massive fuel leak on the right side of the engine. The fuel leak was due to fractured engine fuel lines, and the fuel was leaking at a rate of 11 ton per hour. And once after some time, after approximately 4 hours from the takeoff, the pilots received a error message, the fuel imbalance message. So what they did is, like in the case of Concorde, they manually switched on the crossfeed system. So what happened was the fuel from left started to flow to right, but you shouldn't do the crossfeed when there is a, if you suspect a fuel leak, you shouldn't do crossfeed. So it was the error from the pilot side. They should have seen that the fuel is leaking and shouldn't have done that crossfeed. So right now the fuels, both the fuel in the left tank and right tank are depleting. So the engine from the right tank first cut it off, and later the engine from left also flamed out. So it was about 35,000 feet when both engine was flamed out. So then what they did was they created over a 2 record in this time. From 35,000 feet they made an unpowered glide. It was for about 120 kilometer, which is about 75 miles, and they landed safely. About all 300 passengers were unharmed. So the second record was they had the then record fine from Canadian. I mean, they had to pay a huge fine for this. So yeah, thank you.
Any questions, Ranjapa?
In fact, it's a very difficult topic. Connecting fuel consumption to, sorry, it's a very difficult topic to connect fuel consumption to the stability. In fact, other way around and this way around also. You took up the challenge and did very well, pretty well. Well done. Well done.
As the group captain pointed out, this is one area where it's very difficult to get data. You've done a really good job in terms of getting it. Also, I like Yale's work with the animations. It wakes us up. So it's good to utilize these tools, which are anyway available so easily and freely. Yeah. Thank you. Good.
Good afternoon, sir. We are Team garuḍā, myself, Abhishek Misra. We are going to explain today how variation in load affects static stability. As already in our continuing PPT, we have discussed about what static stability is. That is having a tendency of going back to equilibrium position after any disturbance. Okay, so directly going to how variation in loads affect static stability. For this, we have considered 5 type of loads that we have broadly classified into 2. One is aerodynamic load, another is weight. So for any flight during at any course of flight, it will be having these 2 only, aerodynamic as well as weight. For weight, sir, we have considered 4 fractions, that is crew weight, passenger, payload. Third is fuel mass, and fourth is structural. Structural, more or less, it will be during entire flight, it will be remain constant, but fuel, passenger, payload and crew may change. And coming to fighter aircraft also, their crew weight may be considered as negligible, and or payload and crew can be combined together. So there will be broadly 3 categories: payload and structural as well as fuel mass. So we are going to discuss how these variations in all these 4 loads going to affect static stability. For that, our main consideration is that all weight distributions will finally result in center of gravity. Okay, as well as aerodynamic load will give us neutral point. These 2 will go to the static margin, that is position of center of gravity minus neutral point minus CG, and that will govern static stability, how it's going to change that. Okay, that will be further discussed by my teammates.
Now, as I explained earlier, that the load distribution affects directly to longitudinal static stability. Let's see how it does it happen. So basically, weight contains 4 components, as explained also earlier: empty, crew, payload, fuel. And now we can directly see that we have defined xcg at which the moment of all these due to all these loads is 0. And we can directly see from the formula that if there is a change in weight or position in their position, then the xcg is affected directly, which I will explain further how does it affect stability. Now basically let's look at the aircraft mission profile. Generally what happens is that when we take like particular mission profile, the empty weight, crew weight and payload weight is generally almost constant, but what happens with fuel weight? So here, this is like historical data. As we can see, this is a mission profile: takeoff region, climb, cruise, descent and loiter, and then landing. The data here is taken from historically that the takeoff weight is around 0.97, then climb weight ratio is around 0.985, and then landing 0.995. As you can see that these values are less than 1. So we can directly conclude that the weight is like continuously decreasing, which is generally the fuel weight. Now, after landing, there is only empty weight, which is generally structure weight or avionics weight. Now, this is also taken like from the historical data. How does the empty weight with respect to total weight affect? Now, as we can see, empty weight fraction, WE up by W naught, and on x-axis we have gross weight. The variation is linear. But the key point to note is that the weight fraction is decreasing with respect to W naught. It does not mean that the empty weight is also decreasing. So basically what happens is that empty weight also increases if gross weight increases, but the fraction decreases. Now, as we can see from that formula, that the WE upon W naught is equals to A, W naught C, KVS. Here the A and C are statical constants and KVS is nothing but it is also a constant which is based on variable sweep. If the variable sweep is constant, then K is 1. If it is not constant, then it is 1.04. Now, as we have seen the change in weight and the xcg, how does it affect? Let's look at the static margin. Now, due to the change in payload or their location, the xcg can change. And as you can see here directly, that static margin, which tells about the static stability region, if the xcg moves left of neutral point, then it is unstable. So when a designer is designing an aircraft, then he should make sure that the xcg shift does not make it fall into the unstable region. Now, this static margin stability is like there is some trade-off, which will be explained by my teammate further.
Good afternoon, Ashish here. So let's look at what is the hidden cost of stability. So as we all know, for a stable aircraft, we need to have the center of gravity forward of the neutral point of the aircraft. But this poses a problem in the sense that in case, so what we textbook says, if you increase the static margin, you will be having a more stable aircraft. Okay, fine. But let's look what happens. What are the repercussions of that? So if we increase the static margin, there will be a more nose down movement of the aircraft. And to counteract that, you need to have a downward force on the tail of the wing. So so you need to have a negative lift on the tail of the aircraft. So as we can see, the lift generated by the wing is the summation of the weight and the tail downward force. So you need to produce more lift on the wing. Now, if you produce more lift on the wing, so our CL is increasing, and as given by the law, the induced drag, which is CL square by pi E AR. AR is the aspect ratio. So your induced drag will increase. So this induced drag will effectively reduce the range and the speed of the aircraft, and as we will see. So there is one more aspect is that usually what we'll be having is a longitudinal variation in load. We will study how the longitudinal variation in load affects the static stability of the aircraft. But let's look what happens in fighter planes, where often there is a variation in load laterally. So what we see here is a fighter aircraft which is having a store a weapon on the right wing of the aircraft on the starboard side. So what will be happening is, to counteract this weight, there will be a rolling moment. To counteract that, you need to push the aileron downwards on the right wing of the aircraft. So for that, as you increase, you need to generate more lift, and that you need to generate a negative lift here. So once you increase the lift on the right side, your induced drag increases. And once the induced drag increases on the right side and decreases on the left, there will be an asymmetric adverse yaw will be generated, because once you have because if you are increasing the induced drag, so what will happen is that this will be having a more drag on this side and lesser drag on this side. So it will try to yaw by itself. To control that, you need to have you need to deflect your rudder. So basically, you need to deflect the rudder, and now the problem comes once the store is being separated. So till now, your aircraft configuration is such that you need to balance this. The moment it drops out, suddenly it's like a tug of war when the opponent was there holding it and suddenly he's nowhere. So suddenly you have to ensure that the aircraft is stable again. So that is also very challenging in such cases. So another thing is what happens, let us look at what happens when the aircraft, like suppose, is coming for a takeoff or for a landing. So during those cases, it needs to flare up. So what is flare up is basically you need to ensure that the nose of the aircraft is pointed upwards so that the nose wheel of the aircraft doesn't impact directly while it is landing. In that case, now what happens is that since the wind is coming on the aircraft wing, it will be pushed downwards. Because of the downwash, it will be going down. So it will be like the lift, the wing will be increasing the lift, the angle of attack by alpha, and then it will be going downwards. So usually what happens, this is fine when the aircraft is in air. But what happens when it comes towards the ground? In that case, the negative lift which will be provided by the tails will reduce, because now this ground is cancelling that downwash of the aircraft. So in that case, suddenly what will happen is, even if you pull your elevator controls, the nose up moment will not increase that much. So this will be this can cause a critical failure. So aircraft, the pilots have to be very much aware that you don't cross that limit.
So coming on to the next slide, I'll explain how gradual shifts in weight affect the longitudinal stability of the aircraft. So as we all know, aircraft carry significant amount of fuel for long ranges, and that the weight of the fuel is significant compared to the total weight of the aircraft. And as aircraft flies, the fuel is consumed and the weight is reduced. So this reduction in weight shift the CG. It can shift after forward, backward, after forward, depending on the configuration of the aircraft. So this shift should be accounted for while designing the aircraft. Otherwise, the shift in CG might be such a way that aircraft is not recoverable from the unstable position. Aircraft might become unstable. So this is a CG envelope which shows a weight of the aircraft for the CG index. CG index is nothing but a scaled value of a moment which is calculated from a datum, and it shows nothing but if the CG index is high, the position of the CG with respect to the position of CG is aft of the reference point. Or if the CG index is less, the CG position is forward. So that's what it shows. So how this is done is the how to like account for the shift in CG while designing is giving enough margin in the static margin. That is, static margin will have lower bound and upper bound. So to say the values for typically for cargo aircraft, it will have a static margin from 5% to 15%. Passenger aircraft. So basically when they take off, they'll have a static margin around 15%. As the fuel is consumed, CG is moved aft and the static margin goes up to 5%. This is how the aircrafts are certified to fly in the safer static margin region where the stability is not compromised as well as the performance is also not compromised. So this is the case of gradual shift in CG. Now we'll see what happens when there is an instantaneous shift in CG and how it should be accounted for. This can be seen in military cargos or military cargos as well as fighter aircrafts where they drop a significant amount of payload for a critical mission. So when they are dropped, the shift in CG can be forward or afterward or the forward depending on the location of the bomb or the payload. So usually in military aircraft, fighter aircraft, you have seen the bombs and the payload are carried below the wing, which is like the close to the location of CG. So they ensure that when the payload is dropped, the CG shift is not so significant, because if the CG shift is like very high, no amount of control power can bring back the aircraft to the stable state. Aircraft can go unstable and not controllable. Even if you have thrust vectoring or bigger tails, all moving tails, they might not be efficient if this shift is not accounted for. And these are some of the cases where you see the shifts in CG, and these are some real cases. So in the cargo aircrafts, usually the payload is loaded in the aft region of the aircraft, so that the static margin while takeoff is very less. It will be around close to 5%. And this is done because as already mentioned, if you have higher static margin, the induced drag is high, and the induced drag is high, the range will be less. So since while having less static margin, the induced drag will be less, and they can have higher range. That's one case. And when the payload is dropped in case of missions, so the static margin increases, it doesn't decrease, and aircraft will become more stable, which is not a problem. And in if you see bombers, like it is a B-1 bomber from America, and see when they are dropping bombs, they are not dropping from only one section. They have two compartments. One is aft CG and one is forward CG, and they drop in such a way that CG shift is minimum, and it will not affect the performance of the aircraft. The further part will be explained by.
So thank you, Shri. So as my teammates have already discussed about the how CG shifts with increase or decrease of weight. So now I will explain about how static margin changes with respect to engine placements. So first one is a wing mounted engine. So if our wing is mounted forward on the wing, then our CG shifts forward and static margin increases. So as the static margin increases, our longitudinal static stability increases. So in this case, and we have tail mounted engine as well. So in case of tail mounted engine, CG CG approaches towards the neutral point. So our static stability decreases in this case. So now we can talk about fuel burn and tank location. So if our tank is near the CG, that is if our tank is in the wing, then due to the fuel burn, the CG shift is minimal in this area. But our CG shifts, but CG shift is minimum. So we can say that our static margin remains constant. And if our tank is in aft tank, then in this case, so our weight our weight decreases in the aft part. So CG moves forward, and our static margin increases, and our longitudinal static stability increases in that case. So now,
Okay. So hello everyone. Now as we have seen the variation of load, apart from the weight, there is another load that an aircraft experience, that's aerodynamic load. Now I'll cover there are multiple phases in which aircraft go through. I'll talk about each and every phase and will tell you how the aerodynamic load varies. So first start with the takeoff. Now what happens during the takeoff is that we deploy the flap, and because of we deploy the flap, we have increase in CL and we have increase in camber. Now because of that, there is an increase in lift. Now as we know that increasing lift will cause a movement, and that will be a pitch down movement. Now we have to balance that movement, and we can balance it using our tail. So the tail has to produce a downward force as explained by the Ashish sir. But in order to balance the vertical force, we again need to balance our lift. So therefore, there is a difference in a variation of load when we are taking off apart from when we are cruising. Although this doesn't cause any difference in the static stability, but if we are increasing CL, we have to be careful about the VN diagram and what is the stall CL we have. So that's one thing. And second phase is when we go to the cruise. Now this is an extreme case, but this is important. When we cruise and we have a Mach number increases, after a particular point, we see that our center of pressure changes from 0.25 C to 0.5 C, as we have discussed in our early PPTs. Now what happens, because it's shifting backward, so this will increase our static margin, and this increase in static margin will cause a difference in the stability, and it will again cause us to pitch down. But in this point, the movement, the force generated by the tail is not that significant, because the change in movement here is happening because there is a change in the arm length, and the change in arm length is not as significant as the available arm of the tail. So although there is an increase in there is an increase in stability, the variation of load is not much significant. The last one is the maneuvering. Now when we are maneuvering the aircraft, the lift of an aircraft often increase, the load factor often increase, and because of this there is a large number of load in a wing. Because of this large load there can be a twisting in the wing. Now I'm not saying that twisting will only increase or decrease the aircraft, it depends on your design, but most of the cases the way we design it, when it twists we cause the angle of attack to decrease. uh, because if we increase the angle of attack it may cause a stall, so we prefer that angle of attack should decrease when we want to twist. But as we know that twisting will cause us a structural failure, so this is the point where the structural stability can be compromised when the lift is increasing a lot. Moving on to Sanket.
Hello everyone, my name is Sanket, and the last phase will be the landing phase. Here also, like before my flaps, my slats, and all the configuration of the aircraft is changing, there will be effect and changes in the aerodynamic load. But also because my landing gear is being deployed and the structural weight configuration is changing, there will also be a slight shift in the CG. Hence, also when the aircraft is taking off, there is actually it is completely filled with fuels. But during landing, my fuel ratio will be less than 1 because like I have burned fuel from point A to point B. Hence, the stability or the or how the aircraft behaves when a command is given, it will be different from that of the takeoff to that of the landing. Hence, the pilot has to compensate for it. But in case what happens is that suppose there is sudden changes in the CG part, as in case of dropping of bombs and anything, the pilot can't compensate it directly. In that case, computers are actually used so that it can configure the aircraft so that it can remain statically stable. Also, in case of Concorde, when as said by Kaustubh, that when we go from subsonic to supersonic, the my stability point actually changes. Because of which, in case of Concorde, what happened was that it had a nose heavy movement, or the nose was actually pitching down when it was going from subsonic to supersonic. To compensate for it, the computers actually transferred the fuels from the trim tanks. What was the trim tanks? It was like there was 13 tanks in the Concorde, but some tanks were one was placed in the nose section and other was near the tail section. And when it was transitioning, the fuel from the forward or the nose tank was actually shifted to the tail tank so that it can shift the CG, and hence my aircraft can remain stable in the configuration. So this was for my team. Thank you.
Any questions for Team garuḍā? On one of the slides you mentioned the center of pressure shifts from 0.25 to 0.5, going from subsonic to supersonic. Is that center of pressure or aerodynamics?
It's centers.
Okay, but are there conditions where both will coincide?
For a symmetric airfoil, both will coincide. Center of pressure is the C by 4, and even the aerodynamic stability is C by 4.
Okay. Apart from the loads, you generally classified into the aerodynamic loads and the weight-based loads, right? But there is also the thrust load, as you saw from the previous group's presentation. How does that change some of the conclusions that you made?
Moments.
Yeah, the thrust also generate moments. But if there is a, as already mentioned, there is asymmetric thrust, it will affect the lateral static stability or the lateral motion of the aircrafts. But for the pitching and pitch up, the longitudinal motion, the thrust during the takeoff, landing will be different, because during the takeoff, let's say if you have seen the fighter jets taking off, they'll have afterburners on, and so that they can climb higher. The movements will be different. But basically, if you have seen aircrafts, the thrust line, the thrust line and the CG will be mostly coinciding, except for the passenger aircrafts, because they have like complications. The engine will be mounted down. But for the military aircrafts, the CG line coincides with the thrust line, so the movement is not that much. They ensure that the movement is not that much, and during the design also they have to ensure that when the thrust is changing, the movements are being they are countered if they don't want that movements. Want to add anything?
While talking about the weight versus static margin, you had a quadrilateral. That one. So can you explain why it tapers down with the larger weight, which means that you're allowing for a lesser static margin? What is the logic behind that?
I think this is flight envelope, so this is for it's not a fluid.
this is, see what is happening is with the weight of the aircraft it will cause more changes. Make a slide in.
So as the payload weight is increased, sir. So the shifting, it's small change in the.
This is the gross weight.
Yeah, so
right?
gross weight. As the
Yeah.
gross weight increases,
Hmm.
shifting weight will cause significant change in the center of gravity. It shows like how forward or afterwards. So it's a limit. If the aircraft weight is like let's say 30,000 kg, the shifting CG like the payload carried, the shifting will be limited. But if the payload is very high like has a high weight, then the shift will cause major shift. It will cause higher shift in CG. So that's how I think it's drawn. I guess. I'm not 100% sure.
So you followed what he is.
W is height that allowable shift will be left because effective movement has to be.
Okay, thank you. Sure.
You have one more question. Sir, 4 o'clock.
Yeah, right.
So we have to reach giant attacks.
Yeah, correct.
So asking like, leave early or.
Yeah.
Because if the return gets filled, we'll not get.
I know. It's a long distance. And none of you are attending the talk in the J. Tata auditorium by the other two group captains other than this. You're okay with presenting? Okay, anyway, those who want to leave can leave. You can check with our video recording later. We'll just try to finish this group because we are. Thank you. He said he'll give it on Wednesday.
Wednesday.
This print was given to Chinna, sir. This print was given to Chinna Baba.
I see, okay.
He had kept it there.
Okay.
We forgot. No problem.
Oh, it's the same, right?
This is color, sir. There's a lot of difference, sir. It's another one.
It's okay.
Actually, it's okay.
Okay, sir. Sure, no problem.
I forgot that it was kept in the lab.
Okay.
The topic in general is that what's it?
You have the microphone with you?
The topic for today is that
Hold it in a hand in which you don't gesture, okay? I've seen a lot of people talking and the volume keeps increasing, decreasing. I have to spend a lot of time in editing trying to equalize the volumes. So, most of you, if you're right-handed, then hold your microphone in the left hand. Also, there's a magnet. If you want to just put it on your clothing, that's fine as well, okay? So, do whatever is comfortable to you, but don't keep increasing and decreasing the distance of the mic.
Oh, that image we forgot to remove. That left image. Okay.
Come again?
That image we've had to remove. Forgot. Sorry. What effects does the following have on the static stability? So today we will be discussing on static stability, and our topic is on thrust coupling. So thrust coupling as such in literature it is defined only for longitudinal stability, but we'll be covering how thrust affects directional, longitudinal as well as lateral stability. And already static margin has been discussed, so that includes everything, supposed to be including thrust also if thrust is active. We'll have a neutral point change if there is a thruster also effectively we'll have a different, because we have a force, and then the trimming and other characteristics will depend on thrust. So thrust is an important factor, and thrust is the one which drives, so it's not a small force which can be neglected. And obviously most of the cases you will not have thrust which is coinciding with CG, so you will have movements and that will affect the stability. So that is the topic for discussion today. And my group mate Harika will start with stability.
So aerodynamic static stability is the ability to generate restoring forces and momentums to
Speak a little louder, please. Yeah.
Aerodynamic static stability is the ability of aircraft to restore, to generate restoring forces and momentums to get back to the equilibrium position, the initial response. So there are three types: static, positive, neutral, and negative. So if after a disturbance, if the restoring force and momentum are such that it comes back to the equilibrium position, then it is positive, and if does not, then it is neutral, and if it is opposite, then it is negative. Almost all of these were already discussed. So, and the most favorable is that if the dou CM by dou alpha is negative, because if the aircraft is moving and the angle of attack increase, it has to come back to its equilibrium position. So to come back to its equilibrium position, the moment has to be such that the angle of attack decreases. So it decreases when the CM by C alpha is less than 0, and it increases which is unstable if the CM by C alpha is greater than 0. So, and these equations will be arrived from moment equation equilibriums, and these terms of xCG and xAC, or distance to CG and aerodynamic centers, and these the H terms are converting them from the CG, X terms were notations from nose, and the H terms were notations from converted to CG. And then the rest is Bhagyashree.
Good afternoon, everyone. This is Bhagyashree. So mainly I'll be defining thrust coupling in much detail. So before that, let me go through the basic terms and definitions. So there are four major forces acting on an aircraft in flight: thrust, drag, lift, and weight. It is very basic. And so these are the axes that are defined. Along the fuselage, this is x-axis. Then y-axis positive towards the right wing, and then vertically downward we consider it the z-axis, positive z, and accordingly the roll, pitch, and yaw moments are defined. So there is center of gravity is a basic term. That is the point at which the total weight of the aircraft acts. Then there is the thrust line. So line of action along which the engine thrust force acts, that is known as the thrust line. So for this aircraft configuration, it will be along the plane of symmetry, it will be like this. And then the moment arm, that is the perpendicular distance between the line of action of a force and the CG. So defining the thrust coupling, it is generation of a pitching moment due to engine thrust when the thrust line does not pass through the aircraft CG. So here we can see, generally we see that engines are mounted below the wing, and if the thrust line is not passing through CG, there is an offset in this z-axis. So this offset results in a pitching moment, which is the result of thrust coupling. So next we will see how this thrust line and CG is related to each other, and how we can play around with it to define the stability.
So this is a simple schematic showing
showing the result of thrust line offset from the CG. So the pitching moment are caused by two specific forces. That is the thrust that is being generated by the propeller device, and second, the normal forces acting on the propeller, which we'll see later why they exist. Thus the magnitude of change of the pitching moment with respect to the angle of attack depends upon two coefficients: the rate of change of thrust coefficient with respect to CL and the rate of change of normal force coefficient with respect to CL. Now the thrust coefficient has the particular form in which it depends upon the propeller efficiency and the lift coefficient in the manner like it depends upon CL raised to 3 by 2, but the propeller efficiency also drops with the angle of attack, and hence what we see is a linear growth in the coefficient of thrust with respect to the coefficient of lift. These two effects couple in to make it behave linearly with respect to angle of attack. Second, the P factor is the phenomenon in which there's a thrust asymmetry, not just thrust, we'll see later, the asymmetry of forces on the propeller blades. So in this paper they have analyzed two specific forces. Like if the propeller plane is at an angle of attack and we break the oncoming velocity into two components, one being the normal one and one being the one passing through the plane of propeller. Now as this normal component hits the propeller blades, there are two kinds of forces that are being produced. One is the stagnation point flow that flows radially outwards from the center of the blade, center of the propeller, and another being the drag that is being produced as it flows past the propeller blade. Now they integrated this function where Q is the resisting torque being produced due to the drag of the velocity component into the plane of the propeller, and psi is the azimuthal angle of the blade, and thus N is the normal force that is being produced on the blade, while Fr is the radially outward force that is being produced due to the stagnation point flow. And this radial asymmetry causes a yaw moment on the propeller aircraft, while the normal force causes a pitching moment. And yeah, so then next is the slipstream effect. That there are two effects that come into picture when the air flows past the propeller plane. One being due to the higher velocity of the slipstream, it causes a downwash angle, which increases with the angle of attack because of the normal forces, which itself increase with the angle of attack, thereby deflecting the slipstream downwards. And another being a stabilizing effect that is the result of the dynamic pressure ratio, as the dynamic pressure would be much lower on the tail section than in the free stream. The rest would be covered by Surbhi.
Okay, so last two slides were like mathematical take on some effects. So I'll be summarizing on the thrust coupling effect on thrust effect in general, not like coupling word will not use. Thrust effect on longitudinal stability, then directional and lateral stability. So this is less mathematical because each thing would involve again that is beyond the scope of the 12 minutes we have. So on longitudinal stability, okay, based on usually the wings are mounted, engine is mounted as a lower than the CG. So in typical aircraft, the CG is ahead, but that can depend. So on longitudinal stability, as we can see that engine obviously is not, thrust doesn't pass through the CG, and when thrust increases or decreases, that will create an additional pitch up moment if it is a low wing, or pitch down moment if it is otherwise. and which we'll need to for any increase, it is 10 minutes. Oh, okay. So if you want to throttle, that would also create additional moment, which we have to again take care from control surfaces. So the tail also has to take care of that. So when say this is a typical as in this is just a depiction, not the actual number, just a plot. That if you have a power off versus power on mode. So if it is power on for low mounted engine, you would have an additional pitching requirement, and that would change your effective trim angle of attack. And so that is one effect which will come in CMCG, that will shift the curve, and then the slope again. So if it is a say the thrust is constant, otherwise like effectively approximately constant, but if it is a propeller aircraft, again with respect to angle of attack, your thrust will change, and thrust into R cross F, that will again change. So there will be a derivative of dou T by dou alpha also. So dou Cm by dou alpha term also will again depend on thrust. So not just the trim angle of attack, which is just parallelly shifting, the slope also will change if the thrust is varying with respect to angle of attack, which is a very common thing for propeller aircraft. So both ways you will have a change in the Cm as well as dou Cm by dou alpha curve, which will affect your static stability. So the direct effect is what we have discussed, that it will directly create the moment, and based on the like location with respect to CG, it will create a pitch and down moment. Another some few indirect effects are that if there's a jet or propeller, and if we have a alpha, beta. So if you have a alpha, and then the propeller, the outward velocities will be along the thrust line axis. So there will be a normal force, which we can actually say to be sort of a drag force, but there will be a normal force which will be felt in one side of the container, like the nacelle. So that would again change the that would again create a normal force, which will again indirectly affect the pitching moment. Which will same thing will translated in yaw also if you have a beta. And then there's some indirect effect is that what Papu told, that due to the downwash of the engine, you will have a higher dynamic pressure at tail or like rear control surfaces, as well as the downwash angle. So that will again change the stability of longitudinal stability of the aircraft. Similarly, how thrust affects directional and lateral stability. So for directional stability, there are again the same normal force. If it is beta, then you will have one opposite side, which will again, if CG is here, it will again give a rise to a destabilizing moment. It will increase beta. Then again, slipstream effect, and then asymmetric blade effect. So the last, that P factor which Apu told, that like if you have a rotating disc like this, so here you will have, and if you have a like say beta or angle of attack, so the lower velocity, if you have a beta, then it will lower, if it is pitching down, so the lower part of the engine, the propeller blade which is coming down will have an effective higher dynamic pressure, because the effective velocity is higher, but the one which is going up, it is this side, it will be lower. So there will be a thrust imbalance. So overall the thrust direction, like if you see, it will not pass through the center, it will adjust because based on beta or alpha. So this again will create an axisymmetric thrust, and which will have to be balanced with either trimming using rudder or elevated rudder, sorry. And then yeah, so this is for directional. And then lateral, if you see, so you might have, I mean, if somebody has tried RC planes or something, when you hold and you start throttling, you will again feel like it is twisting, or like all of a sudden you will get a jerk sort of in rolling. So that is like anything you have, then you have a reaction. So if you are trying to increase the RPM, you will feel a just like opposite reaction in your body, which is a rolling. So that might not be very much high, but it will be felt certainly. And then spiraling slipstream. So one effect which will have is, if because of the reaction and the effective, if you have some beta, there will be an effective v velocity, as well as like because of r omega, there will be a helical sort of velocity downwash, which will be felt. So which will then again create an asymmetry in the incoming stream for the surfaces, wing and tail. So that will again affect the stability, as well as jet exhaust. So jet exhaust again, if you have a jet exhaust, the dihedral effect will again be modified, because the engine wake will be asymmetric if you have a beta. So this is for roll stability. So how the thrust affects directional, roll, as well as longitudinal stability. Now, if you change thrust, what will happen? So say you are going cruising and you have fixed your you have trimmed on some because of some thrust, but now you want to modify thrust. So if you reduce thrust again, you will have to if you just simply reduce for a low wing, say, so you will get a pitch down moment. Then you will have to again change your again deflect your elevator such that you balance it out. So each throttle will be again added with the control surface deflection. So you cannot simply throttle. It is all coupled. So that is what thrust coupling is. And then if say one engine is cut off, that in an extreme case, so there also same thing. You will have to which is typically the design parameter, that if one engine fails also, you should have your control surface should have the capability to land safely and do the maneuvers. So that is one more thing where thrust is thrust is a major factor which affects your stability, and that has to be taken care of. Now, design consideration to manage the thrust coupling. That will be discussed with by Maiko.
Hello, I'm Maiko. So there are some design consideration because of such phenomena. So what I've taken an example of a low hanging engine aircraft, which is typically the configuration of all the commercial liners. So you have a thrust which is coming from the downwards, from the downside of the aircraft, and it will cause a pitching up moment. So what you should, while you're designing, basically this is conceptual design, so what you should be doing is have the thrust line as close to the CG as possible, because that would obviously minimize the moment and that will minimize the effort that is to be put to neutralize it. So of course there are some limitations, so that you can't just blindly go to the center line. So minimize this as much as possible, and if it is not possible to do it, then we have our tail, horizontal tail, which will help in neutralizing the moment. So the moment equation is written here, and the corresponding coefficient equation is also written here. So we can see that the tail is what will actually help in neutralizing that moment. So the tail is actually our main control effort. So overall our design should be such that first of all the moment is not much, and if it is there, the angles which the horizontal tail need to be deflected, neutralize the moment should be within the limits and not too high, because you'll have other effects because of the high angles, such as slow separation and etc etc. So you must not go beyond the limits of the tail as well. So again, the CLT is equal to dCLT by d alpha and into alpha plus eta. So alpha is the angle of attack of the entire aircraft, and eta is the trim angle of the horizontal tail. So this has to be adjusted and should be within the limits. So that is the design consideration as far as the conceptual design goes. But of course we have realistic considerations such as structural design consideration or accessibility of the engine as well, because the low hanging engines are also because of the accessibility of the engine while maintenance. So the next we have some case studies and some more points that will be covered by Pragya.
Okay, so here are some advantages and disadvantages of thrust coupling. First advantage is that we have advanced maneuverability. So in fighter jet, the engine is positioned so that the thrust naturally helps the pitch up moment. Automatic trim assistant. So in this, it retrims the plane, so the pilot workload is lesser. For stall conditions. For UAV and cargo planes, thrust coupling can help rotate the aircraft and during the takeoff and landing. So, disadvantages: static stability reduces. The control will become more complex, so we have to add some high-end softwares to manage that. And again, if the nose pitches up too high, then it will be dangerous for the pilot to manage. So there are not exactly case studies, but two cases where Boeing 737. What happened here is that we have the thrusters. We have the engines downside, so the CG shifts downwards, which causes the pitch up moment. So what happened in Boeing 737 MAX was there was a wrong MCAS signal signal by MKS, which caused the crash of the plane. And then another thing, fighter jets have again the same reasons, CG shifts downwards, and for that the pilot has to adjust it by thrust vectoring. So they have to just adjust according to the CG location. Then the conclusion, so whatever it is, yeah, thanks.
I couldn't clearly understand what you were trying to bring out in the difference between the Boeing and the fighter
Not a
jet.
difference. These are two different cases. I was trying to tell.
Come again?
Basically, so this is a
Yeah, can you use the mic?
In the 737 MAX, we know that it was grounded back in 2018 and 19, right? So basically, what they had is because they had modified the design from the main 737. So the engine, while takeoff, had they were angled in such a way that during takeoff they had a pitch up tendency that could stall the aircraft, potentially stall the aircraft. So they put a fly-by-wire system which will actually pitch down the aircraft to avoid that. But the thing is, there was some malfunction or some error in the code that was causing the aircraft to pitch down normally also. So yeah, that is one of the reasons. That is one of the case studies regarding that pitch up thing because of the thrust coupling. And of course, we had the the Boeing face controversy and all that is also there. So yeah, that is that aspect. And for the F-22, and I think
Not a case study.
Automatic, there's no system movement. And even the pilot didn't know that the system was there. And caused a totally fatal accident.
pilot was not aware.
Okay, thank you. Yeah, please.
Do you know what is the specialty of the bomber design, B2 bomber?
B2 bomber design. It has.
Because you presented something related to throttle longitude. What is the specialty of B2?
So B2 bomber, first of all, there is no vertical tail, so exact there is no inherent yaw stability, but it can use the air brakes to yaw the aircraft.
They have throttle, quadrant throttle.
Okay.
So they can manipulate the power to create that yaw.
Okay.
So that is one location where you can use. I mean, they have used the throttle as a control directional stability and to yaw.
Okay. Yeah, I thought it was air brake, but I read it. Okay.